Okay, so good afternoon, everyone, and welcome to the Cryosphere Pavilion. My name is Ana Gomes, and I work as a researcher at CIMAR in Portugal, and I work with Arctic marine bacteria. Today, I'm here to present our afternoon session titled Melting the Arctic, Insights from Scientific Research in the Svalbard Archipelago. And with that, I would like to give the floor to our first speaker, Dr. Hugo Nani.
Thank you, Anna, and good afternoon, everyone. I will give you an overview of the research that has been conducted in Svalbard and especially at the research station of Ny Alesund. This presentation is done in collaboration with Ingrid Skjerstad, which is the research coordinator at the Ny Alesund research station from the Norwegian Polar Institute. And myself, I'm a researcher at the University of Oslo, and I'm working in Svalbard and in the Alps to look at the stability of glacier and also the role in the hydrological system. As you can see here on the picture, both Ingrid and me spend a lot of time in the field. And today, the presentation I wanted to share with you is how science is conducted in the field, what are the outcomes, but also how climate change is happening up there in the Arctic. You can see in this map that has quite an original representation with a little star that shows the location of Svalbard, an island very close to the North Pole. And this is where the Ny Alesund research station is located, which is one of the northernmost research stations and actually one of the northernmost places where people are living in the Arctic. This place is really important, both because it is very close to the pole and the polar region, but also because it is one of the fastest regions on Earth. In this map, you can see that everything is red. It's showing the warming since the 80s. And you can see that all over the Arctic, and especially in Svalbard and in this region where you have the green arrow, climate warming is up to 7 times more than what's observed on average over the globe. That's why we often refer as Svalbard as the canary in the coal mine, which is an indicator of climate change, which could also be seen as an early warning place at what is going to happen in the future in the rest of the world. So today I will take you both to Svalbard, but after presenting you this, it's also maybe a step into our future, depending on our current action and on our current pathway. Let me take you to Ny Alesund, which is a research station where the Norwegian and many institutions across the world have been conducting research for the past 50 years. It's quite a unique place because it's a bit like here at COP today, where you have a lot of different countries that try to work together in a common direction and that are helped with both permanent staff, but also a lot of scientists. So this is where science in the Arctic is really important. The 4 parts of my presentation today are 4 of the components of the cryosphere, because as I told you, Svalbard is so close to the North Pole that we have almost all of the components of the cryosphere. I'm not going to talk about ice sheets, even though we have some ice sheets in Svalbard. But I'm going to present you the latest research on permafrost, sea ice, glacier, and snow, and especially how these components have been affected in the past year by climate change, but also how it has changed the livelihood and the way we conduct science in the Arctic. Let's first start with permafrost, where more than 20 projects have been happening in the Ny Alesund research station, which means 20 different teams have been going there to study the impact of permafrost. If we take a look back, you can see here in this map with the polar projection that show the organic carbon contained in the permafrost. Why the permafrost is important at the global scale? It's because it contains so much carbon that if it's continued to be melting, it will significantly contribute to global emission. That's why it needs to be taken at the global scale, even if it's happening so far from where we are today. And indeed, the permafrost is melting, and especially the permafrost is projected to continue to melt. In this graph, again, you can see the location in Svalbard in the little arrow. You can see how much permafrost will be left depending on the different scenario and depending on the action and the negotiations that are actually taking place today and might end tomorrow, with an agreement that will determine how much permafrost we will have left in the coming years. The red color show if we continue business as usual, meaning that we lose more than half of the current permafrost. As I told you, this will have impact on a global scale, but today the focus is also at what's happening to people living in the Arctic, and especially the scientists. The science that we conduct in Ny Alesund is also greatly impacted by climate change. And here I wanted to share with you, and you will see in the next slide, what's happening at this base, and the people living there are directly affected by the climate change. They have been observed that everything has been becoming much more unstable, that much more money was needed to protect and change the infrastructure, and therefore that also the way of life of scientists in the Arctic has been changing. We can see also in this picture that it requires a lot of investment, a lot of manpower, and people working on this. And of course, this is happening on the research station, but it's also it's happening all over the Arctic and will soon be happening much more in our region if we have the melt of the permafrost. So let's say that the permafrost has been melting quite drastically. And that's why you can see that I've changed from the very nice picture of the permafrost to the actual impacts. And you will see progressively in this talk, all of this picture being changed to what's happening in the Arctic. Next, I will present you some research on glacier, where most of the projects are actually conducted next to the Ny Alesund research station, and more than 60 teams have been working on it over the past 5 years. You can see in this picture a very gray, very dark and very sad glacier. It was taken recently in Longyearbyen, very close to Ny Alesund, also in Svalbard. And it really shows that glaciers have lost their protection, which is the snow, and most of them are totally melting. By the end of the century, we might reach 10 degrees of warming in Svalbard, which is, as I told you, a place that is warming so fast, which means that by the next 400 years, we might lose all of glacier in Svalbard. Of course, this has impact on a global level, and this is going to happen also on other places. But as we lose the glacier in Svalbard, we also lose the memory we have associated to them. And here I wanted to show you some historical pictures that have helped researchers to reconstruct what's happening in Svalbard, and really to highlight why is it important to have such places where we can monitor the cryosphere, when we can monitor the environment and therefore see the changes that are currently happening there. So all of these pictures have been taken in the 30s, and they have been used combined with extensive field work by a team of a Norwegian researcher and many colleagues to really show the loss of mass of glacier in Svalbard and how they will be projected by the end of the century. So again, this is an highlight of how long-term research, field-based research, really helps to understand what's happening now, and of course, what is going to happen in the future. But as we lose the glacier, we also lose the memory of what has been happening. I wanted to share with you a very recent project that has happened in Svalbard. I was there doing field work. It's part of the Ice Memory project. So the Ice Memory is a team of scientists, policymakers, philanthropists. So it's a very cross-generational initiative that aims at preserving the memory of our climates. Because as the snow is falling and forming glacier, it's trapping the air into the glacier, and therefore recording the climates. There was a drilling last April that was aimed to safeguard the climate of Svalbard and the information about this. However, while this drilling was still quite successful, as you can see this in the picture, there was managed to recover some of the ice core. As the climate and the glacier has been changing in Svalbard, it was also much more difficult to study the glacier, to study the climates. Some of us got stuck in melting glacier in the water. Crevasses are increasing. And what I want to highlight here is that as climate change is continuing and continuing, it's also changed the way we do science. But it also highlights how people in these regions and in all of the other regions where we have the cryosphere will be suffering by the climate change. For us scientists, it might be easier to cope because of the funding we have. But for people that really need to live in these places and depend on this environment, this will be drastic changes to their way of life. And of course, we will lose such kind of environments. So as I told you, now we have glaciers that is becoming, water ponds, permafrost that is destabilizing structure. And let's move to sea ice, where a little bit of the research is also conducted in Ny Alesund. And first, I wanted to show you this animation that is not working. So I will go directly to what we observe in the field and what we project. This picture is showing you how is the sea ice looking now in Svalbard from the last spring next to Ny Alesund. And the projection you can see show you the rests and the remaining sea ice that we will have in the Arctic, depending on the scenario. So the red line shows that where we don't have any more sea ice. And you can see that most of the projection actually projects that we will lose all of the sea ice in the Arctic, independent of our action today. Of course, it will be better if we stabilize at 1.5, but the sea ice and the Arctic sea ice is almost already committed to be lost by the end of the century. And this has drastic impact, of course, on the Arctic amplification. For instance, that's why Svalbard is warming so fast. But as I told you, I want to also show you the local impact. And here you have two pictures. The picture on the left was taken maybe 20 years ago when scientists were still able to use their snowmobile to conduct their research from the research station to the glacier. It was taking approximately 20 minutes just to drive straight to the glacier. While today, you can see in the other picture, they need to take a boat and takes much more time to reach the glacier. It's much more hazardous. And of course, this kind of shift are happening all over the Arctic region. So sea ice is almost fading and committed to be lost. And now let's move to the last component I wanted to show you today is snow. And for this, we will move a bit away from Ny Alesund. We'll move to Longyearbyen, that is the main city in Svalbard, where we have almost 2,000 people living there. And in Svalbard, most of the land is covered by snow, but the time of the year where we have snow is gradually reducing, meaning that we have a wetter and warmer climate. But this loss of snow is not only affecting the glacier, it's also affecting the way of life of the people living in this region. And a few years ago, there was an avalanche in Longyearbyen that was very surprising. And just recently, a few months ago, the governor of Svalbard, which is the main local authority, just released a report saying that there is an increasing risk of wet snow avalanche in Longyearbyen, which really shows that this changing climate is not only affecting the environment, but also the people living there. And with this sentence that climate change has been there and changed the premise for planning really show that local population needs to adapt and already need lots of investment for adaptation. In this picture, you can see what was wiped out by the avalanche and that really destroyed a lot of houses and caused also human casualties. And this was very unexpected. In this figure, where you have a lot of color, what's important is that if you look at where the avalanche has been happening, this is where it was totally unexpected. So as climate change is progressing in the Arctic, we are facing more and more change, but we are also facing more and more unknown. What we know is how to avoid further damage of the cryosphere and further increase in temperature. This we know how to do. We need to cut the emission and stay below 1.5. What we don't know, it is what is going to happen if we continue further and further, and how it will happen to people living in this region, but also way outside the region. Because as all of these regions are changing and destabilizing, this is also, as I told you, an early warning of what is going to happen all over the world, as what is happening in the Arctic does not only stay in the Arctic, as you can see in this map, where everything is connected. And with this clear message of saying that whatever is happening up there is going to impact everything, I would like to give the floor to my next presenter that will give you further insight on how climate change has been changing the glacier up in Svalbard. Thank you. So now I would like to give the floor to Dr. Gabriel Kleber, if I don't make a mistake, that has been living many years in Svalbard to conduct research.
Great. Thank you, Hugo. I am Gabrielle Kleber. I am a postdoc at the University of Tromsø in Norway. But the research that I'm presenting today, I did actually during my PhD at the University of Cambridge, which I just finished up this past summer. So this is just an example of one of these research projects that's going on in Svalbard that Hugo already spoke to you about. And so I'll just jump right into it. But so methane is a topic that's becoming increasingly prominent here at COP. And the reasons for that, I don't really need to explain to people in this room, but I will touch on it a little bit. Methane is a really strong greenhouse gas. In fact, it's about 36 times stronger than carbon dioxide. And that means it absorbs a lot of heat and retains that in our atmosphere. It's been responsible already for about a quarter of the warming that we've already experienced. And the concentrations of methane in the atmosphere are rising. They've already nearly tripled the pre-industrial values. And they are steadily increasing at alarming rates. But there are large uncertainties in the future projections of methane emissions, and that's actually due to natural methane emissions. And that's because we have these climate-sensitive systems like wetlands and permafrost that continue to release more and more methane as they continue to warm. And so what we're seeing here is something called a positive feedback loop. And that's where the climate warms. It allows these climate-sensitive systems to release more emissions, which accelerate and exacerbate climate change. But the problem is these feedback loops are really difficult to identify. They're difficult to predict, and they're really difficult to quantify. And that means they're largely unconsidered in our climate models and our carbon budgets. So the Arctic is particularly vulnerable to increasing global temperatures. And to make things worse, it's warming up to 4 times faster than the rest of the world. And so that means the climate-sensitive systems that we find in the Arctic, like glaciers and permafrost, are already experiencing dramatic impacts from a warming climate. And with that comes many feedback loops. And methane plays an important role in this, and that's because we have a really large reservoir of carbon stored within the Arctic. We have about 1,300 petagrams of carbon stored within the permafrost, and we have about 21,000 petagrams of carbon stored beneath the permafrost. I know these are really large, very arbitrary numbers, but if I put them into context by telling you that we have only about 780 petagrams of carbon in our current atmosphere, you can see that the release of even just a small fraction of this carbon could have potentially large implications to our global climate. But this carbon right now is stored beneath something we call a cryospheric cap. And that's where glaciers and permafrost create this kind of frozen barrier that seals in the carbon beneath. But of course, these glaciers and permafrost are vulnerable to a warming climate, and they're threatening to allow this carbon to be released to the atmosphere. In fact, we're already seeing emissions from permafrost, as Ugo mentioned, and we suspect that if we continue emissions as they are, that about 120 petagrams could be released by 2100. And that means that translates to a warming of almost 0.3 degrees Celsius. Now, the subpermafrost emissions are a bit trickier. We know that the potential for the methane from these subpermafrost reservoirs is happening, but we don't understand the quantity or the timing of this just yet. There's a lot of uncertainties involved in this. So a few examples of these kind of climate sensitive emissions that we're seeing from subpermafrost reservoirs we're already aware of are, for example, from high latitude lakes. So this is where we have lakes in places like Canada and Alaska that are allowing for the permafrost to degrade beneath them and allowing for some of this like deep-seated sub-permafrost methane to be released. We're already seeing about 16 teragrams of methane from these lakes released every year, and we expect that by the end of the century, we'll see an increase of more than 50%. We also have something called gas emission craters, particularly in Russia. And that's where we have methane gas building up beneath and within the permafrost. And eventually it builds up enough pressure that it just causes this large kind of catastrophic explosion. And it leaves behind these craters that are dotting the Russian landscape. And these craters allow for sustained emissions long after this blowout happens. I'm sorry, but it looks like the text is a bit cut off here in this projection. And finally, we know of submarine seeps. This is where we have the disintegration of permafrost at the seafloor due to warming seas, and that's allowing for methane to vent at the seafloor. We know of more than 7,000 seeps just in the Barents Sea, and we expect that there are seeps located across the rest of the Arctic. So what I'll discuss today is a paper that we published earlier this summer on a new mechanism of deep-seated methane release that we've discovered in the Arctic. And that is actually in the form of glacial groundwaters. So okay, things are projecting a little bit differently, but that's okay. So I'll give you a bit of a background on how this kind of mechanism works. So if we go back in time to pre-industrial times, when glaciers were large and at their kind of big, healthy extents, we had this cryospheric cap where the permafrost extended beneath the glaciers, and that kind of trapped in groundwaters and methane beneath them. We had groundwaters sourced from melt at the base of the glacier, and methane was introduced to these groundwaters through both the biological production of methane, but also through interaction with rocks that store methane in them, particularly rocks like shale. And so all of this was kind of stuck between this cryospheric cap. But if we go forward in time, we've had these glaciers retreat and expose land. We see that we have kind of a patch of unfrozen ground that's been exposed by the retreat of the glacier. And that's just effectively a hole in this cryospheric cap. And that is allowing the discharge of these groundwaters, and along with that, the discharge of methane, which is being emitted directly to the atmosphere. But these groundwater springs are able to flow year-round. And what that means is that during the winter, they form these large kind of icing fields in the area in front of glaciers. And these icings can be several meters thick and several kilometers square in area. And these are the systems that we study. So I will take you back to Svalbard, just as Hugo's already shown us where the study is. And that this is actually the fastest warming region on Earth, as he mentioned. It's warming about 2 or 2.5 times faster than the rest of the Arctic. And what's also staggering about Svalbard is that it's already lost about 30% of the volume of its glacier since the last 80 years. And our fieldwork is based up on Svalbard, actually in the town of Longyearbyen, so a bit different than the Ny Alesund settlement that Hugo discussed. This is a settlement of about 2,500 people, and it has only about 35 kilometers of roads. And that means we rely on snowmobile and ski to get around to do our field work and to access these glaciers. But of course, not every day is blue skies and sunny. So we have many days where we're in whiteout blizzards, and we rely completely on GPS to find these glaciers and find our field sites. We also, as Hugo showed you, deal with poor snow conditions very often and spend a lot of time digging snowmobiles out of snow and waterlogged snow. We also deal with very cold temperatures. We've sampled at temperatures down to minus 42 Celsius, and we are sampling liquid water. And at these temperatures, that acts like super glue, so it makes our work very challenging. And of course, as many people know, we deal with the constant risk of polar bears. So that is something that we have to remain vigilant throughout the fieldwork. So our goal was to sample as many of these groundwater springs as we possibly could in front of as many glaciers as we possibly could. We managed to sample from 78 different glaciers, and with that we found 123 different springs. We covered an area about the 10th the size of the full archipelago of Svalbard. And how we've done the sampling is we arrive at the glacier, we find this large icing that I've described, and then we drill into it until we reach this pressurized water that comes out. We can take some initial measurements of this water, but eventually we take vials of this water and take it back for later analysis in the lab. And what we found in these 123 springs that we measured was ubiquitously high concentrations of methane. So all but one of the springs was supersaturated with methane, with concentrations up to 600,000 times the atmospheric equilibrium concentration. And what that means is that once this water reaches the surface and starts interacting with the atmosphere, it immediately starts releasing methane directly to the atmosphere. And if we add a geological map to this map, we see that the highest concentration springs, so the ones with the largest bubbles in this map, are congregated in areas depending on the geology. And we see that the highest congregation of high methane hotspot springs are within areas where we have Jurassic and Triassic shales. Now, this is no surprise because shale rocks contain a lot of methane in them. And we see that this geological control is statistically significant. And what this means is that we can be pretty confident that this methane that's being released from these groundwater springs is tapping into this large, deep reservoir of subpermafrost methane. Now, we weren't surprised when we found that these springs were as highly concentrated in methane as they are. And that's because when we do the sampling, we can often ignite the gases that are released from these springs. And that is due to just the significant amount of methane in these systems. But of course, what's really important in the grand scheme of things is how much methane are these springs actually releasing. And so we've calculated that across the Svalbard archipelago, we think there's about 2.3 kilotons of methane being released. Again, I'm showing you an arbitrary number, but if I give you some context, might help you get a feel for what that means. So this is equal to about 8% of Norway's annual oil and gas related emissions. For more visual context, it's about the same as 230 million party balloons of methane being released to the atmosphere. It's equal to about what 30,000 cows released per year. And for a more local example, it's about 65,000 camels. So the scale of these emissions on Svalbard are not yet alarming. But what is concerning is that this deep reservoir of carbon extends throughout the Arctic. So we can certainly expect that these emissions are also happening in places like Greenland and Canada and the Russian Arctic. We can also expect that these emissions will continue to grow as glaciers continue to retreat. So we wanted to look into how these emissions might increase. And so we expanded our study to look at a different kind of glacier. So the whole study that I've discussed so far has been focusing on what we call a land terminating glacier. So that means the whole glacier is situated on land. The terminus of it ends on land. And this is opposed to a marine terminating glacier. And that's where you have the main body of the glacier located or situated on land, but it extends all the way down to the sea, and its terminus ends in the sea. So we decided we wanted to look at if marine terminating glaciers would be a future emission source. So the concept behind this is quite similar to the land terminating glacier. We have this subglacial groundwater that has methane being introduced to it, and then it's being released in front of the glacier. But while the glacier ends in the sea, this groundwater is being released into the sea. And when it's emitted into the water column, it's quickly consumed by bacteria and other microbes in the water column. And that means that the methane doesn't actually reach the surface, or at least not much of it reaches the surface. But once these marine terminating glaciers melt enough and retreat enough that their terminus now ends on land, they've opened up this space for the groundwater to retreat, to be released onto the land. And we have this terrestrial point of methane released direct to the atmosphere. And what's concerning is that we've already seen that 7% of the Arctic's marine terminating glaciers have transitioned into land-based in the last 2 decades. And that's expected to increase. And so we studied about 3 different marine terminating glaciers. We performed or took some gridded samples in front of these glaciers where we drilled into the sea ice and sampled the surface water beneath the sea ice in kind of this gridded fashion. And we found that we have hotspots of methane concentrations in front of the glaciers, implying that there are these groundwaters releasing in front of these glaciers, just in the subsea kind of force field in front of the glaciers. So we can expect that as these glaciers retreat and eventually end up on land, that we will see these groundwaters released terrestrially. So of course the question is now, do we need to worry about these emissions? We need to worry that these emissions are out of our direct control. Once this mechanism has been initiated, which it already has, it's not something we can stop or reverse. The only thing we can do is slow down the rate at which they're increasing by drastically reducing the emissions that we can control. We should worry that there is a massive geologic reservoir of ancient methane and that these groundwaters are tapping into this methane that's been stored in the rocks for millions of years. And this subpermafrost methane is effectively a seemingly endless reservoir of methane that will allow the emissions to continue and increase as long as we allow it. We should worry that glacier melt is accelerating across the Arctic, and also that more and more marine terminating glaciers are becoming land terminating. And that means we're opening up more land area for these groundwaters to escape. We should worry that despite all of this, we are still approving new licenses for fossil fuel drilling in the North Sea. Just last month, we approved 27 new licenses. We should worry that despite all of this, we are still subsidizing the oil industry at record-breaking levels. It's $7 trillion just last year. And we should worry that we are still questioning whether or not we should be aiming for 1.5 degrees C, despite the science showing that we need to be aiming for well below that. That's it. Thank you.
Yes,
Sure.
I have questions for both our distinguished speakers today. Starting with Dr. Nani. Yeah, might as well start with that actually. You're there already. Two questions for you then. Are these emissions that are coming from these spring water, are they detectable by space-based measurements?
We're not sure. On Svalbard, no, but there has been indication that there might be detection that we've been able to detect methane at the margins of the Greenland ice sheet, but nothing has been confirmed. We have not done any ground truthing with that, but we're not sure.
All right. Second question. These so when water comes out the glacier or just actually happens, it's more ice system, right? Have you slid down any of these? Like kind of on the slide, have you slid down that slide?
Not completely, but I have slipped many times, but we usually wear like crampons or spikes so that we have some traction on these, but driving a snowmobile over them can be quite tricky.
It looks like it could be potentially quite fun.
Yeah, unfortunately I haven't taken advantage of that.
Yeah. Well, actually, we have no questions. For Ugo, you said that the average snow cover days in Svalbard will be increasing 3 days per decade. I feel like it's actually kind of low compared to other regions in the Arctic, but maybe I'm wrong. How does it compare to like other parts of the Arctic in their annual snow cover days increasing?
So it depends on which part of the Arctic you compare with. Svalbard is still quite north compared to most of the places in the Arctic, meaning the threshold from rain to snow, it's still quite far. So if you talk about like the Siberian Arctic, then the temperature are already so close to the threshold that you can reduce a lot the number of days with snow cover. While in Svalbard, it's still quite cold, so it takes more time to reduce this threshold.
All right. Yeah.
Thanks.
Any questions from the audience?